For the longest time, physicists have been chasing this dream, right? A single theory for everything.
Absolutely, this grand unification quest.
And we've pretty much nailed it for three of the fundamental forces. Electromagnetics, strong, weak. Quantum mechanics handles them beautifully.
Mm-hmm.
But then there's gravity.
Ah, gravity. The elephant in the quantum room, you could say.
It just refuses to play by the same rules, doesn't it?
It really does. Einstein gave us general relativity, which is, spectacular for describing planets, galaxies, the big stuff.
Right, works like a charm.
But it's fundamentally a classical theory, and when you try to mesh it with the quantum rules that govern everything else, especially in extreme places like black holes or the Big Bang,
The whole thing just breaks down.
the math, yeah, it becomes non-renormalizable, basically. You can't make sensible predictions at those scales. It's a huge roadblock.
Okay, so that's the setup. And today we're diving deep into some really fresh research, a totally different angle on gravity.
That's right. An approach that tries to bring gravity into the fold, make it look a bit more like the other forces described by the Standard Model.
And for you listening, we know you want the insights without, drowning in equations.
Yeah.
So we're going to pull out those key aha moments for you.
Exactly. We're looking at a paper called Gravity Generated by Four One-Dimensional Unitary Gauge Symmetries and the Standard Model by Mikko, Partanen, and Jukatulki. And there's a popular science piece about it, too.
So our mission today, unpack this new idea, get a handle on the core concepts, and talk about what it could all mean.
Sounds good.
Okay, maybe let's quickly revisit the Standard Model first, just to set the stage. It uses these things called gauge theories, built on symmetries.
Precisely. Gauge theories are, they're foundational. The idea is that the laws of physics have certain underlying symmetries, like the outcome of an experiment shouldn't change if you, say, rotate your setup.
Oh.
Now, when you demand that these symmetries hold locally, meaning they can vary from point to point in space-time, something amazing happens. You need force-carrying particles, bosons, to make it all work.
So that's where photons and gluons come from.
Exactly. The photon for electromagnetism, the W and Z bosons for the weak force, gluons for the strong force. And these Standard Model gauge theories have been incredibly successful. A key reason is that they're renormalizable.
Renormalizable. That word again, like you can calculate things properly at any energy scale.
Sort of, yeah. It means the theory doesn't break down when you push it to higher energies. You don't get uncontrollable infinities popping up everywhere. We can make solid predictions.
And gravity isn't.
Gravity, when treated in the standard way as a gauge theory of space-time symmetries, is non-renormalizable. That's the core difficulty. You try to calculate things at very high energies, like near a singularity, and the math just explodes.
So you can't predict what happens.
Not reliably, no. We use things like effective field theories, which work fine at lower energies, but they're incomplete. They don't give us the full quantum picture.
Which is why finding a quantum theory of gravity is, the holy grail.
Pretty much, yeah.
Okay, so enter Partanen and Tulki. They're suggesting gravity doesn't come from space-time symmetries, but from something else, these unitary symmetries.
Exactly. This is the radical departure. They propose gravity arises from four one-dimensional unitary gauge symmetries. Think U1 symmetries, kind of like the one in electromagnetism.
Okay, U1 symmetries,
Yeah.
but not acting on particles in the usual way.
Well, they're acting within a more abstract mathematical space. They use what's called an Eight-Spinor formalism.
Right, you mentioned that, Eight-Spinor.
Yes.
Standard Model uses four-component spinors for things like electrons, doesn't it?
It does, Dirac spinors. So this theory essentially doubles that. It works with objects that have 8 components. This richer mathematical structure is key.
And these U1 symmetries act within this Eight-Spinor space.
Yes, they operate on this structure. The researchers are careful to call them U1 symmetries of gravity to distinguish them, but mathematically they behave like the U1 groups we know. They also use these 8x8 bosonic gamma matrices within this framework.
Okay, gamma matrices, mathematical tools.
Right, tools to define how these 8 spinors transform and interact. And from these gamma matrices, they derive something they call kernel matrices, labeled Ta.
Kernel matrices, what's special about them?
They have some neat mathematical properties: constant, traceless, Hermitian, unitary, involuntary. Lots of jargon, I know. But here's the kicker, the really big aha moment. These 4 kernel matrices, just from their mathematical relationships, they naturally form a representation of the symmetry group, U1, isn't it?
U1, I say that sounds very familiar. Isn't that the electroweak symmetry group from the Standard Model?
Bingo! That's exactly the symmetry group underlying the electromagnetic and weak forces.
Wow. So this structure just pops out of their gravity framework.
It pops out of the math related to these kernel matrices derived from the Eight-Spinor structure they're using for gravity. It's a really profound connection they've uncovered. It suggests gravity might be linked to the other forces at a much deeper level than we thought.
That is intriguing. Okay, so they have these symmetries. How do they actually make gravity happen? They introduced this space-time dimension field.
Yes, exactly. To connect these internal symmetries in the Eight-Spinor space back to our physical space-time, they proposed this new fundamental field, IG. It has 4 components.
4 components, like space-time dimension.
Kind of conceptually linked, yeah. And crucially, those 4 U1 symmetries act on these 4 components of EG. It's like a new fundamental handle related to space-time itself.
And what do they do with this field?
Well, using this IG field, they can rewrite the Lagrangian density for quantum electrodynamics, QED, the theory of light and matter, but in their Eight-Spinor language.
They rewrite QED. Why?
They call this rewritten version the generating Lagrangian density of gravity. Think of Lagrangian as the master equation that dictates how a system behaves. By starting with the familiar QED Lagrangian and translating it into their new framework, it gives them a foundation.
A foundation to build gravity on.
Precisely. It allows them to see how gravity might emerge in a way analogous to electromagnetism.
So how do these U1 symmetries transform this IG field? What does that look like?
It's a kind of phase transformation. Each of the 4 U1 symmetries changes the components of the IG field by multiplying them by a phase factor, which involves the corresponding kernel matrix and a transformation parameter. If it's a global symmetry, that parameter is the same everywhere.
Okay, global symmetry. But in the standard model, the forces arise when you make these symmetries local, right? When the parameters can change from place to place.
You got it. And they do exactly the same thing here. They take their 4 global U1 symmetries acting on IG and demand they hold locally.
And what happens then?
Just like making the U1 symmetry of electric charge local requires the photon field in QED. Making these 4 U1 symmetries local requires a new field to compensate. And that field turns out to be a tensor gauge field for gravity, which they call Hey. This is their candidate for the gravitational field, emerging directly from demanding local symmetry.
So the gravitational field arises in a way that's very, very similar to how the photon arises in QED.
The mechanism is remarkably similar, yes. The structure of the Lagrangian, the requirement of gauge invariance under local transformations, they draw strong parallels to QED throughout the paper. It makes gravity look much less exotic in a way.
Does this analogy extend further? Like QED has the fine structure, constant, alpha, measuring interaction strength. Do they get a gravity version?
They do. They derive an analogous gravity fine structure, constant, malog, and as you'd expect for gravity.
It's tiny.
Incredibly tiny, something like 10 to the minus 45 for the electron, which, perfectly reflects how astonishingly weak gravity is compared to electromagnetism.
And does the ratio match what we observe?
Yes, they show the ratio of their calculated ag to the electric fine structure. Constant matches the known ratio of gravitational to electric forces between electrons. That's a nice consistency check.
Okay, this sounds really elegant. But to actually use it to calculate things, you need the machinery, right? Gauge fixing, Feynman rules.
Absolutely. A quantum field theory isn't much use without them. They address this. They apply a gauge-fixing procedure, specifically a generalized harmonic gauge, which is familiar from GR studies, to handle the redundancies from the gauge symmetries.
And that lets them calculate interactions.
It allows them to define the Feynman rules. These are the diagrams and mathematical rules physicists use to calculate how particles interact. They lay out the rules for graviton and photon propagators, how they move, and the interaction vertices, how they connect and influence each other.
So they have the tools. Can they use them to check if this reproduces, say, Newton's gravity at low energies?
Yes, that's a crucial test. They show that using their Feynman rules in the non-relativistic limit slow speeds, weak fields, you recover Newton's inverse square law of gravitation.
Good, so it connects back to the gravity we know and experience.
It does. It passes that fundamental check.
Now the big one, renormalizability. Does this approach avoid the problems that plague other quantum gravity attempts?
This is where it gets really promising. They demonstrate that their theory has something called BRST symmetry.
BRST, what's that?
It's a specific kind of symmetry that's known to be a hallmark of consistent renormalizable gauge theories, like the Standard Model. Having BRST symmetry is a very strong hint that a theory is renormalizable.
A hint? but not proof.
Well, they also back it up with some explicit calculations. They present results for one-loop renormalization, which is the first step in checking for renormalizability, and those results are consistent. It suggests this framework might indeed lead to a well-behaved quantum theory of gravity.
Okay, that's potentially huge. What about Einstein's equivalence principle? The idea that gravity and acceleration feel the same, how does that fit in?
It's handled in an interesting way at the quantum level. They find that mathematically, the inertial mass and the gravitational mass of a particle get renormalized slightly differently by quantum effect.
Oh, so they aren't automatically equal.
Not automatically from the math alone, but they then impose the equivalence principle as a physical condition. They require that the final renormalized values of inertial and gravitational mass must be equal. So the principle holds, but as an imposed condition on the renormalized theory.
Interesting nuance. They also mention something called TGRW, teleparallel gravity.
Right. TGRW, teleparallel equivalent of general relativity. It's another way to formulate Einstein's gravity. Instead of using space-time curvature, like standard GR, it uses something called torsion, which is like a twisting of space-time.
Okay. Different math, same gravity.
Essentially, yes. And Partanen and Tolke show that if they choose a specific gauge fixing within their theory, the Weizenbuck gauge, their field equations become equivalent to those of TGRW.
So even though they started with completely different symmetries, these U1 things, instead of space-time symmetries, they end up describing the same classical gravity.
Exactly. Their theory in the classical limit, and with that specific gauge choice, aligns with TGRW, and therefore also with standard general relativity. It shows their framework is compatible with known classical gravity.
And the goal isn't just gravity, right? The paper title mentions the standard model.
Yeah.
Can they fit the other forces and particles in?
That's definitely the ambition. The framework, with the Eight-Spinor formalism and the space-time dimension field, is designed to be broad enough to potentially incorporate all the standard model particles, quarks, leptons, and their interactions, strong and weak forces, alongside gravity.
So one unified mathematical language.
That seems to be the hope, yes.
You mentioned their gauge symmetry. The U1s acting on the Ig field is different from the symmetry in standard TGRW. Can you clarify that difference?
Yeah, it's a key distinction they emphasize. Their theory's gauge symmetry involves these compact U1 groups. Think of compact like a circle you go around and come back to where you started. Standard TGRW, on the other hand, is usually based on the non-compact translation group in tangent space, more like moving along an infinite line, you never come back.
Why does that matter?
Because the gauge symmetries in the standard model, like U1, SU2, SU3, are also compact groups. So the symmetry structure of their gravity theory looks mathematically much more like the structure of the standard model than traditional approaches based on space-time symmetries or non-compact groups.
Ah, so it feels more unified in its mathematical DNA, so to speak.
That's a good way to put it, yeah. They're using similar types of mathematical building blocks.
Okay, let's pull this all together. What are the absolute key takeaways from this deep dive?
Well, first, it's a genuinely novel approach to gravity. Using these internal unitary symmetries within an Eight-Spinor framework is different.
And crucially, it seems to build bridges to the standard model.
Yes, that's perhaps the most exciting part, especially the emergence of that U1 AU2 structure from the kernel matrices. It hints at a deep unity.
A potential clue to unification.
A potentially very strong one. And importantly, it also seems to work on a practical level. It reproduces Newtonian gravity, and it shows signs of being renormalizable, potentially solving that huge quantum gravity problem.
Thanks to things like BRST symmetry.
Exactly. And those initial one-loop calculations are encouraging.
But it's early days, right? Lots more work needed.
Oh, absolutely. This is cutting-edge theoretical work. It needs much more rigorous investigation, detailed renormalization proofs, exploring cosmological consequences, really pinning down how the gravity U1s connect to the standard model's internal symmetries. Many open questions.
Definitely sounds like a fascinating path forward, though.
It really does.
So maybe a final thought for you, our listener, to chew on. What if gravity isn't the odd one out? What if it's fundamentally built from similar principles to the other forces, just expressed differently? If this path, or one like it, leads to a truly unified theory, imagine the aha moments that could unlock about reality itself.
It's a tantalizing prospect, and for anyone wanting the really deep dive, we'll make sure the links to the paper and other resources are available.